everyone, welcome back to my channel. In this video, we are going to study about linear differential equation and reducible to linear differential equation that is called as a Bernoulli's form. First, let us understand linear differential equation of first order and first degree and the problems related to linear differential equation. First, let us understand what is linear differential equation. A differential equation of the form dy by dx plus p of x into y, which is equal to q of x, where p and q are the function of x, is called linear differential equation. That means linear differential equation is a differential equation that is of the form dy by dx plus p of x into y, which is equal to q of x, where p and q are the functions of x, is called as a linear differential equation. This is the definition of linear differential equation. Next, we shall see how to find the solution for a linear differential equation. What is the procedure to find the solution for a linear differential equation? First step, write the given differential equation of the form dy by dx plus p of x y, which is equal to q of x. Here we have to note that the given problem is of the form dy by dx plus p of x into y, which is equal to q of x. That is a first step. Next step, find the integrating factor by evaluating integrating factor, which is equal to e power of integral of p into dx. Here we already discussed about what is the definition of integrating factor in the previous video. After finding the given differential equation of the form dy by dx plus p of x into y, which is equal to q of x, then we have to find the integrating factor using the formula e power of integral of p into dx, where p is a function of x. Once we obtain the integrating factor, the general solution for the given differential equation is given by the formula. Here we have to remember this formula, y into integrating factor, which is equal to integral of q into integrating factor into dx plus some arbitrary constant c. Here q is nothing but here this function, and integrating factor we have to obtain using the formula e power of integral of p into dx. Here this is a general solution for a given differential equation. This is a procedure to find the solution for linear differential equation. You have to remember this formula. Here integrating factor is nothing but y into integrating factor is e power of integral of p into dx, which is equal to integral of q into e power of integral of p dx into dx plus c. So this is a solution to obtain a linear differential equation. Here this is a procedure to find the solution for linear differential equation. Next we have a note here. If differential equation of the form dx by dy plus p of y into x, which is equal to q of y, where p and q are the function of y, then the solution is given by, here previously we find the differential equation of the form dy by dx plus p of x into y, which is equal to q of x, where p and q are function of x here. But in this case, here x is an dependent variable and y is an independent variable. In that case, the differential equation of the form dx by dy plus py into x, which is equal to q of y, where p and q are the function of y. In that case, to find the solution for a linear differential equation, the formula is given by x into integrating factor, which is equal to integral of q into integrating factor into dy plus some arbitrary constant c. For this, integrating factor is x into e power integral of p dy, which is equal to integral of q into integrating factor is exponential power of integral of p dy into dy plus c. This is a formula to find the solution for a given differential equation. If the differential equation of the form dx by dy plus py into x, which is equal to qy. Don't confuse with these two differential equation. First differential equation of the form dy by dx plus p of x into y, which is equal to q of x. But in this case, the differential equation of the form dx by dy plus py into x, which is equal to qy. So the solution for a given differential equation is x into exponential power integral of p dy, which is equal to integral of q into exponential power integral p dy into dy plus c. This is a formula to find the general solution for a given differential equation of the form this. Let's see how to solve problems on linear differential equation. Here is the first problem. Solve dy by dx plus y into cot x, which is equal to cos x. Here solution, the differential equation of the form dy by dx plus p of x into y, which is equal to q of x, where p and q are the function of x. Here from this given problem, P is given by, here this is of the form dy by dx plus y into P of x, which is equal to Q of x, where P is cot x and Q is cos x. Therefore, P is equal to cot x and Q is equal to cos x. Using the given differential equation, we have to find P and Q value first. Next step, after obtaining P and Q value, we have to find the integrating factor. We know that integrating factor is given by the formula exponential power integral of P dx. In the previous note, we have find the differential equation of the form dx by dy plus py into x is equal to qy. In that case, integrating factor is exponential power integral of p into dy, because p and q are the function of y, but here p and q are the function of x, so integrating factor is given by exponential power integral of p dx. You have to observe carefully. Here p dx is integrating factor. Next, substitute p value here, we get as integrating factor, which is equal to exponential power of integral of p is cot x into dx. We know that integral of cot x dx is given by log of sin x. Therefore, substitute the value exponential power log of sin x. Here exponential and log gets cancelled, the remaining is sin x. Therefore, we get an integrating factor as sin x. Once you obtain the integrating factor, then the general solution for a given differential equation is given by the formula y into integrating factor is exponential power integral of p dx, which is equal to integral of q into integrating factor, that is exponential power integral of p dx into dx plus c. Substitute integrating factor value and q value here, we get as y into, here integrating factor value is sin x, which is equal to integral of, here q is cos x, substitute cos x into, here this value is sin x into dx plus c. Here in the next step, we have to expand the integration. Here integral of cos x sin x dx, we don't know the value, so to make the simplification easy, here in the place of this multiply and divide by 2, we get as y into sin x, which is equal to 1 by 2 into integral of 2 cos x sin x into dx plus c. If we cancel these two terms, the remaining is integral of cos x into sin x into dx itself. Now we know that integral of 2 into cos x sin x, this is of the form sin 2x, and substituting that value here, we get as here 1 by 2 into integral of 2 cos x sin x is sin 2x into dx plus some arbitrary constant c. Now we know that integral of sin 2x dx is minus cos 2x by 2. Substituting that value here, we get as y into sin x, which is equal to minus cos 2x divided by 2. Here multiply this 2 inside the bracket, we get as 2 into 2 is 4, hence we get minus cos 2x by 4 plus some arbitrary constant c. So this is a solution for a given differential equation dy by dx plus y cot x, which is equal to cos x. This completes the problem. We shall move on to another problem. Solve dy by dx plus 3x square by 1 plus x cube into y, which is equal to sin square x by 1 plus x cube. First, we have to note that given differential equation of the form linear differential equation or not. Here obviously the differential equation of the form dy by dx plus p of x into y, which is equal to q of x, where p is 3x square by 1 plus x cube and q value is sin square x by 1 plus x cube. After finding p and q value, next step we have to find the integrating factor, which is given by exponential power of integral of p dx. Here substituting p value as this, here we get as exponential power of integral of 3x square by 1 plus x cube into dx. Here we have to integrate this value. Here we have to note that this is of the form integral of f dash of x by f of x into dx, where f dash of x is a derivative of f of x. So in that case, if the derivative of a function f of x is present in the numerator and the denominator is a function itself, in that case the integrator value is given by log of f of x. This is a standard result in integration, that is integral of f dash of x by f of x into dx, which is equal to log of f of x. We have to write log of this function value here. In the same way, here also, here the function is 1 plus x cube. Here we know that differentiation of 1 plus x cube is nothing but, here 1 is constant, so differentiation is 0. Here differentiation of x cube is 3x square, that is present in the numerator. Hence this is of the form integral of f dash of x by f of x into dx. So we can simply write it as exponential power of log of this function value, that is 1 plus x cube. So we get the exponential power of log of 1 plus x cube. In the next step, if we cancel this exponential and log value, we get the integrating integrating factor value as 1 plus x cube. So this is the integrating factor. Once we obtain the integrating factor, the general solution for a given differential equation is of the form y into exponential power of integral of p dx, which is equal to integral of q into exponential power of integral of p dx into dx plus some arbitrary constant c. Substituting integrating factor value and q value, we get as y into integrating factor is 1 plus x cube, which is equal to integral of, here q value is sin square x by 1 plus x cube into, here this value is 1 plus x cube into dx plus c. Here numerator also 1 plus x cube, denominator also 1 plus x cube gets cancelled. Remaining is sin square x into dx. We have to integrate this sin square x into dx. We can't integrate directly. So to make the simplification easy, we have to substitute as, here we know that cos 2x value is 1 minus 2 sin square x. Using this formula, sin square x in the place of sin square x, we can write it as, here 1 minus, if we take cos 2x to the right hand side and 2 sin square x to the left hand side, that becomes sin square x is 1 minus cos 2x divided by 2. Hence in the place of sin square x, we can write it as 1 minus cos 2x by 2. Here in the place of sin square x, we can write it as 1 minus cos 2x by 2. Therefore y into 1 plus x cube into integral of, here in the place of sin square x, we can write it as 1 minus cos 2x divided by 2 into dx plus c. Here take 1 by 2 outside the bracket and simplify integration for this 1 minus cos 2x, we get as, here 1 by 2 into, here integration of 1 into dx is x minus, here integration of cos 2x is sin 2x divided by 2 plus c. Next multiply 1 by 2 inside the bracket and simplify, we get as 1 into 1 plus x cube, which is equal to x by 2 minus sin 2x divided by 2 into 2 is 4x plus c. So this is a solution for a given differential equation. This completes the problem. We shall move on to another problem. Solve 1 plus y square plus x minus exponential power of tan inverse y into dy, which is equal to 0. We have to note that the problem is not directly given as of the form linear differential equation. Instead, we have to reduce this equation to one of the forms of linear differential equation. For that, here take this 1 plus y square to the right hand side, we get as x minus exponential power of tan inverse y into dy by dx, which is equal to minus of 1 plus y square. Here the linear differential equation of the form dy by dx plus px into y, which is equal to qx, or we have to reduce this to the form dx by dy plus py into x, which is equal to qy. Here if we take this x minus exponential power of tan inverse y to the right hand side, that goes to the denominator, and if we simplify further, the equation becomes complicated. So to make the simplification easy, take this dy by dx to the right hand side, that becomes minus 1 plus y square into, here if we take this dy by dx to the right hand side, if dx goes to the numerator and dy goes to the denominator, hence becomes dx by dy, which is equal to, here x minus exponential power of tan inverse y as it is. Now if we take this value to the right hand side, that becomes dx by dy, which is equal to, here this goes to the right hand side, here negative value also goes to the right hand side, that becomes here minus x minus into minus plus exponential power of tan inverse y. Take this value first, hence we get exponential power of tan inverse y minus x divided by 1 plus y square. Now if we split this value, we get as exponential power of tan inverse y divided by 1 plus y square minus x divided by 1 plus y square. You have to observe carefully. This is our dx by dy value. Here if we take this value to the right hand side, that becomes 1 plus y square divided by x minus exponential power of tan inverse y. Hence the simplification becomes complicated. Therefore, I take dy by dx to the right hand side, hence we get dx by dy into minus 1 plus y square. If we take this value to the right hand side, if we multiply minus inside the bracket, we get as exponential power tan inverse y minus x divided by 1 plus y square. If we split this value, we get this, that is exponential power tan inverse y divided by 1 plus y square minus x by 1 plus y square. This is our dx by dy. Now take this value to the left hand side, we get as dx by dy. If we take this value to the left hand side, that becomes minus value becomes positive sign of 1 by 1 plus y square into x, which is equal to, here exponential power tan inverse y divided by 1 plus y square in the right hand side itself. Now we can conclude that this differential equation is of the form dx by dy plus p of y into x, which is equal to q of y. So this is a differential equation of the form dx by dy plus py into x, which is equal to qy. Now take the p and q value, where p is nothing but 1 by 1 plus y square, q is nothing but exponential power tan inverse y divided by 1 plus y square. In previous two problems, the differential equation of the form dy by dx plus px into y, which is equal to q of x. But this problem is of the form dx by dy plus py into x, which is equal to qy. Now in the next step, find the integrating factor. We know that integrating factor for the value p. Here p is of the form 1 by 1 plus y square. Therefore, exponential power integral of p into dy. This is an integrating factor. Substitute p value and evaluate the integration. We get as exponential power of integral of p value is 1 by 1 plus y square into dy. We know that 1 plus 1 by y square into dy, this is integration value is tan inverse y. Therefore, this value becomes exponential power of this value is integral of 1 by 1 plus y square is tan inverse y. This is an integrating factor. Once you obtain the integrating factor, the solution for a given differential equation is of the form x into exponential power of integral of p dy, which is equal to integral of q into exponential power of integral of p dy into dy plus c. Substitute integrating factor value and q value over here and simplify. We get as x into this value is exponential power tan inverse y, which is equal to integral of, here q value is exponential power tan inverse y divided by 1 plus y square into this value is exponential power tan inverse y into dy plus c. Now we have to simplify the integration. Here also e power tan inverse y, here also e power tan inverse y. This becomes e power 2 into tan inverse y. In the denominator we have 1 plus y square. We know that differentiation of tan inverse y is 1 by 1 plus y square. Similarly, integration of 1 by 1 plus y square is tan inverse y. So, to simplify the integration, in next step, we have to put in the place of tan inverse y as t. Therefore, differentiating this term with respect to y, we get as differentiation of tan inverse y is 1 by 1 plus y square into, again differentiation of y is into dy, which is equal to, here differentiation of t is dt. Therefore, substituting this value over here, we get as, here in the place of 1 by 1 plus y square into dy, we have to substitute as dt, and in the place of tan inverse y as t, we get as here x into e power t, which is equal to integral of, here this value is e power t into, here this value is also in e power t into, here 1 by 1 plus y square into dy is dt plus c. Now e power t into e power t is e power 2t. Therefore, we know that integration of e power 2t is e power 2t divided by 2 plus c. Substitute t value as tan inverse y. Again we get as x into e power tan inverse y, which is equal to e power of 2 into, in the place of t as tan inverse y divided by 2 plus c. This completes the problem. This is a solution for a given differential equation. So these are all some important problems on how to find the solution for a linear differential equation. We shall move on to another topic, reducible to linear differential equation, which is called as Bernoulli's form, states that a differential equation of the form dy by dx plus px into y, which is equal to qx into y power n, where p and q are the function of x only. This is called a Bernoulli's form. Our aim is to reduce this Bernoulli's form to a linear differential equation form. For that, this equation is reduced to linear differential equation by dividing the above equation by y power n. Here we will observe carefully, here the extra term is y power n. So, to reduce this to a linear differential equation means you have to divide this equation by y power n. We get as 1 by y power n into dy by dx plus p of x into, here we have y term divided by y power n means if we take this y to the denominator and simplify, we get as 1 by y power n minus 1, which is equal to q of x. Now if we divide this equation by y power n, the equation reduces to this. This is not a linear differential equation form. To reduce this to a linear differential equation form, in the next step, we have to take in the place of 1 by y power n minus 1 as u. Here 1 by y power n minus 1 as u. Next step, you have to differentiate this term with respect to x. We get as 1 by y power n minus 1, if you take to the numerator, that becomes y power minus n plus 1. This is up to form x power n, that is n into x power n minus 1, that is 1 minus n into y power, this is minus n plus 1 minus 1. Plus 1 minus 1 gets cancelled, remaining is y power minus n into, here we have to differentiate this y term with respect to x, therefore we get as dy by dx, which is equal to, here also we have to differentiate this u term with respect to x, therefore we get du by dx. Here once if we divide the given equation with respect to y by n, we get this value. Next step, we have to substitute 1 by y power n minus 1 as u, and again differentiate this term with respect to x, we get as 1 minus n into y power minus n into dy by dx, which is equal to du by dx. Now if we take y power minus 1 to the denominator and this term goes to the right hand side, that becomes here 1 by y power n into dy by dx, which is equal to, here if we take this term to the right hand side, that becomes 1 by 1 minus n into du by dx. Now substituting all this value over here, we get as here 1 by y power n into dy by dx. In the place of this, we can substitute as 1 by 1 minus n into du by dx plus p of x into, here 1 by y power n minus 1 is u, which is equal to q of x as it is. Next step, take 1 minus n as LCM and simplify, we get as here du by dx plus here 1 minus n into p of x into u, which is equal to 1 minus n into q of x. Here 1 minus n is some constant term, therefore we can write it as du by dx plus, here this value we can take it as, here 1 minus n into p of x, we can take it as p dash of x into u, which is equal to, here 1 minus n into q of x, we can take it as q dash of x. Now the equation dy by dx plus p of x into y, which is equal to q of x into y power n, that is Bernoulli's form, which is reduced to an linear differential equation form, that is du by dx plus p dash of x into u, which is equal to q dash of x. This is an linear differential equation form. So this is a procedure to reduce the non-linear differential equation form to a linear differential equation form. Once you obtain the linear differential equation form, the procedure is same as before to find the solution for a given differential equation. Let's see how to solve problems related to reducible to linear differential equation form. Here is the first problem. Solve dy by dx minus y into tan x, which is equal to sin x cos square x divided by y square. Observe carefully the differential equation. The given differential equation is of the form dy by dx plus p of x into y, which is equal to q of x into y power n. Here p of x is some minus tan x and q of x is, this is sin x into cos square x, and y power n is, if we take this y square to the numerator, that becomes y power minus 2, that is our y power n. So clearly this is an Bernoulli's form equation. We have to reduce this form to a linear differential equation. For that, take this y square to the left hand side, we get as y square into dy by dx minus tan x into, here y square into y is y cube, which is equal to sin x into cos square x. Call this equation as equation number 1. Now observe carefully, this is an equation of the form x and y. We have to reduce this to an equation containing u. For that, take u is equal to y cube. Here this y cube as u, if we take the y cube as u and differentiate this term with respect to x, we get as du by dx value is, differentiation of y cube is 3y square into, again differentiating y with respect to x, that is dy by dx. Next step, take this 3 to the left hand side, we get as y square into dy by dx. This value becomes 1 by 3 into du by dx. Now substituting this value as 1 by 3 into du by dx and y cube value as u, we get as 1 by 3 into du by dx plus, here take minus tan x as it is into, here y cube is u, which is equal to sin x into cos square x as it is. Next step, take LCM as 3 and simplify, we get as du by dx plus, here taking LCM means you have to multiply by 3, that is minus 3 into tan x into u, which is equal to 3 into sin x into cos square x. Now we can conclude that the given differential equation of the form du by dx plus some p dash of x into u, which is equal to q dash of x, where p dash of x and q dash of x are some values containing x. Therefore, this is a linear differential equation form. So we have to find the p dash and q dash value. Here p dash is minus 3 tan x, q dash is 3 into sin x into cos square x. Once we obtain p dash x and q dash of x value, we we have to find the integrating factor value. That is, integrating factor is exponential power of integral of p dx. Substitute p value and simplify the integration. Exponential power of integral of p is minus 3 tan x into dx. Minus 3 is constant, take as it is, into integration of tan x is log of secant x. Therefore, we get as exponential power of minus 3 into log of secant x. If we take this minus 3 inside the bracket, this is of the form n log m. So this is of the form log n power m. Hence we get log of secant power minus 3x. So exponential and log gets cancelled. If we take this secant power minus 3x to the denominator, that becomes 1 by secant cube x. We know that reciprocal of cos is secant. Therefore, in the place of 1 by secant cube x, we can substitute as cos cube x. This is our integrating factor value. Once we obtain the integrating factor, we know that the solution for a given differential equation is of the form u into exponential power of integral of p dx, which is equal to integral of q into exponential power of integral of p dx into dx plus c. Next step, substitute q value and integrating factor value. We get as u into, here integrating factor value is cos cube x, which is equal to integral of q value is 3 sin x into cos square x into integrating factor is cos cube x dx plus c. Multiply cos cube x and cos square x, we get as integral of 3 sin x into cos square x into cos cube x is cos power 5x dx plus c. Next step, to integrate this value, take cos x as t. Here, if we substitute cos x as t, means if we differentiate this value with respect to x, we get as dt, which is equal to minus sin x dx. Substitute in the place of sin x dx as dt and simplify, we get as u into, here in the place of cos x we have to substitute as t, therefore we get ut cube, which is equal to integral of, here 3 as it is, sin x into dx is minus dt, therefore we get minus 3 into, here cos x is t, hence we get t power 5 into dt plus c. Understand carefully. Here 3 into sin x cos power 5x dx. To simplify the integration, substitute t as cos x. Therefore, differentiating this value becomes dt, which is equal to differentiation of cos x is minus sin x dx. So, in the place of sin x dx, we can substitute as minus dt, and in the place of cos x substitute as t, we get as u into t cube, which is equal to integral of minus 3 into t power 5 into dt plus c. Now, we can integrate easily. Minus 3 is constant, take as it is, into integration of t power 5 is t power 6 by 6. That is u into t cube, which is equal to minus 3 is constant as it is. T power 5 integration is t power 6 by 6. Here 3 ones are 3 twos are. Substituting t value as cos x, we get as, also u value is y cube into t is cos x. Therefore, we get cos cube x, which is equal to, here minus t is cos x. Therefore, we get minus cos power 6x divided by 2 plus c. This is a solution for a given differential equation. This is a procedure to find the reducible to linear differential equation. We shall move on to another problem so that you can understand in a better way. Solve dy by dx plus y into tan x, which is equal to y square secant x. Take the given problem. Here, observing this problem, clearly we can take that the given differential equation is of the form dy by dx plus p of x into y, which is equal to q of x into y power n. So this is an Bernoulli's form equation. We have to reduce this form to an linear differential equation form. We have to divide this term by y square. That is the next step. Dividing equation by y square, we get as 1 by y square into dy by dx plus, here y by y square gets, y by gets cancelled, remaining is 1 by y into tan x, which is equal to secant x. Take this equation as equation number 1. Here, observing this equation, this is an equation of the form x and y. We have to reduce this equation to an equation of the form u. For that, put u is equal to 1 by y. And next step, we have to differentiate this u term with respect to x. We get as du by dx, which is equal to, here differentiation of 1 by y is minus 1 by y square into, again differentiating y with respect to x, we get as dy by dx. Here we have 1 by y square into dy by dx. Substituting this value here, we get as, if we take this minus to the left hand side, we get as, equation 1 becomes, here 1 by y square into dy by dx is minus du by dx plus 1 by y is u into tan x as it is, which is equal to secant x. To remove this minus sign, multiplying throughout the equation by minus sign, we get as du by dx plus into minus minus u into tan x, which is equal to minus secant x. Now, we can observe that the given differential equation reduced to a linear differential equation form. Therefore, the differential equation of the form du by dx plus p dash of x into u, which is equal to q dash of x, where p dash is minus tan x and q dash is minus secant x. Once you obtain p dash x and q dash of x, what's the next step? We have to find the integrating factor and then find the solution for a given differential equation. Therefore, the integrating factor is given by exponential power of integral of p dash into dx. Substitute p dash value over here, we get as exponential power of integral of minus tan x dx. Here take minus outside the integration. We know that integration of tan x is log of secant x. Therefore, we get exponential power of minus log of secant x. Here this is of the form n log m. So, we get as log of secant power minus 1x, that is secant inverse. So, if we take that secant inverse to the denominator, that becomes 1 by secant x. Here exponential log gets cancelled, remaining is 1 by secant x. We know that reciprocal of secant x is cos x, therefore we get as cos x. This is an integrating factor. Once you obtain the integrating factor, the general solution for a given differential equation is given by u into integrating factor, which is equal to integral of q into integrating factor into dx plus c. Substituting q value and integrating factor value, we get as u into, here integrating factor value is cos x, which is equal to integral of q is minus secant x into integrating factor is cos x into dx plus c. Now we have to find the integrating value for this. Here we observe carefully, here secant x into cos x. We know that secant x can be written as 1 by cos x. Therefore, cos x gets cancelled, remaining is 1, that is minus 1. Therefore, you get u into cos x, which is equal to integral of minus 1 into dx plus c. We know that integration of minus 1 is x. Therefore, we get u into cos x, which is equal to minus x plus c. Next step, substitute u value as 1 by y, we get as 1 by y into cos x as it is. If we take this minus x to the left hand side, that becomes plus x, which is equal to c. This is a solution for a given differential equation. This completes the problem. Here is another problem. Solve dy plus x into sine 2y minus x cube into cos square y into dx, which is equal to 0. Here, if we divide this throughout the equation by dx, we get as dy by dx plus x into sine 2y minus x cube cos square y, which is equal to 0. Here, take this value to the right hand side, we get as dy by dx plus x into sine 2y, which is equal to x cube cos square y. Now the given differential equation reduced to an Bernoulli's form equation, that is dy by dx plus p of x into y, which is equal to q of x into y power n. Here this value is y value. So divide throughout the equation by cos square y. That's the next step. We get as 1 by cos square y into dy by dx plus x into sine 2y by cos square y, which is equal to x cube. Next step, we know that sine 2y can be written as 2 sine y into cos y. That is 1 by cos square y into dy by dx plus x into 2 sine y cos y divided by cos square y, which is equal to x cube. Now cos y gets cancelled. Sin y by cos y is tan y. Therefore, we get as here 1 by cos square y is secant square y into dy by dx plus 2a into x into this value is tan y, which is equal to x cube. Now this value is tan y. Here differentiation of tan y is secant square y. Now we can take the u value as 2 into tan y. Here we have to take the u value so that we get this value. In that type we have to take the u value. So take u as 2 into tan y. If we differentiate this value with respect to x, we get as here differentiation of u with respect to x is du by dx, which is equal to 2 is constant, take as it is, into differentiation of tan y is here secant square y. Again we have to differentiate this y with respect to y x, we get as dy by dx. Now we can substitute in the place of secant square into dy by dx as, if you take this 2 to the left hand side, it becomes 1 by 2 into du by dx. That's the next step. It is 1 by 2 into du by dx, which is equal to secant square y into dy by dx. Substitute this value in equation, this equation, we get as 1 by 2 into du by dx plus here 2 into tan y is u into x as it is, which is equal to x cube. If we take this 2 to the right hand side, that is taking LCM as 2 and simplify, we get as du by dx plus 2ux, which is equal to 2x cube. Now the equation reduced to a linear differential equation form, that is dy by dx plus p dash of x into u, which is equal to q dash of x, where p dash of x is 2x, q dash of x is 2x cube. Next step, find the integrating factor, that is exponential power of integral of p dash into dx. Substitute p dash as 2x, we get as exponential power of integral of 2x dx. Here take 2 outside the integration. Integration of x is x square by 2. Therefore, we get exponential power of 2 into x square by 2. Here 2 gets cancelled. The remaining is exponential power of x square. This is our integrating factor. Once you obtain the integrating factor, the general solution for an integrating factor is given by u into exponential power of integral of p dash of dx, which is equal to integral of q of exponential power integral p dash into dx into dx plus c. Substituting q value and integrating factor value, we get as u into integrating factor value is exponential power x square, which is equal to integral of q is 2x cube into integrating factor is exponential power of x square into dx plus c. Here now now we have to integrate this value. Here to make the simplification easy, in the place of x square substitute as t. That's the next step. Put x square is equal to t, we get as, here differentiating this value with respect to x, we get as 2x dx, which is equal to dt. Therefore, substituting this value over here, we get as, here in the place of x square we have to substitute as t. Here if we split x cube as x square into x square value is t and x into dx, that is 2x into dx remaining here. 2x into dx value we can substitute as dt. Therefore, we get as u into, here e exponential power x square is t, which is equal to integral of, here observe carefully, 2 into here x cube can be split as x square into x. X square, in the place of x square we can substitute as t, and remaining is 2x dx. In the place of 2x dx we can substitute as dt. Here exponential power x square is t. Therefore, we get integral of exponential power t into dt plus c. Now we can integrate this using integration by parts rule, taking t as first function and exponential power t as second function. We get as first function into integral of e power t is e power t itself minus integral of second function, that is integral of e power t is again e power t itself into differentiation of t is 1 plus c is an arbitrary constant. Here we are integrating this using integration by parts rule. Next step, substitute t value as x square. Here again we get as, here u value is 2 into tan y, or we can write it as 2 into tan y, which is equal to x square minus 1 plus c by exponential power x square. If we divide throughout the equation by e power x square, we get as 2 tan y, which is equal to x square minus 1 plus c by exponential power x square. This is a solution for a given differential equation. This completes the problem. We shall move on to another problem. Solve r sin theta minus r square into d theta minus cos theta into dr, which is equal to 0. Or in the examination they may ask r sin theta minus cos theta into dr by d theta, which is equal to r square. Take the given problem. Here if we take this value to the right hand side, that becomes cos theta into dr minus r sin theta minus r square d theta, which is equal to 0. Now in the given problem, divide throughout the equation by d theta and take this value to the right hand side. We get as cos theta into dr by d theta, which is equal to r sin theta minus r square. Again we have to divide throughout the equation by cos theta. We get as dr by d theta, which is equal to, here r into sin theta by cos theta is tan theta. Here minus into minus plus. If we take this value to the right hand side, that becomes minus itself. Therefore, we get minus r square into, here if we divide throughout by cos theta means we get as 1 by cos theta. We know that 1 by cos theta value is secant theta. So in the next step, take this value to the left hand side. We get as dr by d theta plus r into, here we get, if we take to the right left hand side, that becomes minus tan theta, which is equal to minus r square secant theta. Now clearly we can observe that this is a differential equation of the form dr by d theta plus p of theta into r, which is equal to q of theta into r per n. So this is a Bernoulli's form of equation in r and theta. So we have to reduce this Bernoulli's form to a linear differential equation form. For that we have to divide the equation by r power n term. Here r power n term is r square here. So dividing throughout the equation by r square, we get as 1 by r square into dr by d theta plus, here r by r square is r gets cancelled, remaining is 1 by r into minus tan theta, which is equal to here minus secant theta as it is. Here we have to reduce this equation to a linear differential equation containing u. For that, put u is equal to minus 1 by r and differentiate this u term with respect to theta, we get as du by d theta, which is equal to, here minus is constant, take as it is, into differentiation of 1 by r is minus 1 by r square, here minus into minus plus 1 by r square into, again differentiation of r with respect to theta is dr by d theta, that is our du by d theta value. Substituting this value over here, we get as, here 1 by r square into dr by d theta is du by d theta plus minus 1 by r is u into tan theta as it is, which is equal to minus secant theta. So this is an equation, that is differential equation of the form du by d theta plus p dash of theta into u, which is equal to q dash of theta. This is a linear differential equation in u and theta form, where p dash is tan theta and q dash is minus secant theta. Once we obtain p dash and q dash value, we have to find the integrating factor value in theta, that is exponential power of integral of p dash into d theta. Substitute p dash value as tan theta, we get as exponential power integral of tan theta d theta. We know that integration of tan theta is log of secant theta, that is exponential power log of secant theta. Here exponential log gets cancelled, remaining is secant theta. This is our integrating factor value. Once we obtain the integrating factor, the general solution for a given differential equation is given by u into integrating factor, which is equal to integral of q into integrating factor into d theta plus c. Substituting q value and integrating factor value, we get as u into, here integrating factor is secant theta, which is equal to integral of q is minus secant theta into, here integrating factor value is secant theta into d theta plus c. Here we know that secant theta into secant theta is secant square theta. We know that secant square theta integration is tan theta, that is u secant theta, which is equal to integral of minus secant square theta d theta plus c. We know that integration of secant square theta is tan theta. Hence we get u into secant theta, which is equal to minus tan theta plus c. Last step, substitute u value over here, we get as, we know that u is minus 1 by r. Substituting that value here, we get as minus 1 by r into secant theta, which is equal to minus tan theta plus c. Or if we take this minus tan theta to the left hand side, that becomes tan theta minus u is 1 by r, that is secant theta by r, which is equal to c. This is a general solution for a given differential equation. So this is a problem containing r and theta. So we have to reduce this to a differential equation, that is linear differential equation. It's a form containing du by d theta plus p dash of theta into u, which is equal to q dash of theta. Once we reduce this form to a linear differential containing u and theta, the general solution is given by this formula, and substituting we get the solution for a given differential equation. This completes the problem. Till here we study about linear differential equation and reducible to linear differential equation and important question paper problems on that. In next video we study about orthogonal trajectories of family of curves. Hope you all like the video. Thank you.